get it. All right, cool. Oof. Today's not one of those good days. All right, excuse my room. My room is a mess. And yeah, okay, all right. So I think what we did for the homework was basically it was the one vector, or should I say the x and y vector, and the answer that you should get if you guys did it correctly. This is the answer. This is the answer that I expect you to give me. Is going to be t squared divided by 2 plus 2t, comma, t squared plus 3t. And if you got a different answer, that means you did it wrong, which is okay. We're here to get it wrong so that I can help you guys correct it. Oh, here comes Ryan. And let me see, I think I got a message from Joe, other Joe. Let me just make sure that I get him right now. Okay. Well, if you guys haven't noticed, my life is sort of a mess at the moment. But it's okay because I'm here. I didn't leave like Daddy left, if that makes any sense.
Professor, is that supposed to be in like vector notation? With the arrows or? Oh,
Yes,
okay.
yes. Sorry. All right, so let's start today's lesson. I think what we finish at 7:30, so we can go to 7:30. If you guys like, we can go longer. Depends on how you feel. If anything, I'm betting you guys want to finish at 7:30, especially since Jace is in fires right now. Okay, maybe I can get one of those cool backgrounds. How do I get a cool background? That's fine, whatever. You guys have seen the innards of my
It's under
room.
preferences. Like you click the Zoom preferences and then you can switch to background and filters. I prefer filters too, because just so I can hide my room as well.
Yeah, so no one can see, the innards of your home,
Yeah, exactly.
especially since my room is a mess. And I'm dying and I can't find it. So pretend you did not see your professor's room today. All right. We're going to start talking about tangent vectors. And tangent lines. Just like we saw in Cal 1, what we do is we take the derivative of our function, and we take the derivative of our function, and we find that the derivative, then we take a point, we plug it into the mx plus b formula, and we basically get our actual tangent line. That's how we're going to get the tangent line. When it comes to the tangent vectors, we're going to divide it by the norm. So what we're going to say is if we're given a smooth curve, and this is actually very, very essential, it has to be a smooth curve. And I'll tell you guys what a smooth curve means because there's an actual mathematical definition for a smooth curve if you guys haven't seen it before. And it's very important that's a smooth curve because if it's not a smooth curve, then obviously we'll have bad points, and those bad points will, how should I put it, not be differentiable. And it's not differentiable, that means you can't actually find the tangent line at that point with the calculus that you guys need. The calculus that you guys know, because then you'll need other means to find it, and those other means you don't have at the moment. Okay, so by saying given a smooth curve, and this is we'll say just put it in like a little boxy like this, R of t is called smooth R of t is called smooth on AB AB being your given interval, if R prime of t is not equal to 0 on AB. So it cannot be equal to 0, which means it cannot be like a hard point. And what do I mean by a hard point? Well, if you recall, the absolute value of a specific function, usually the graph looks like this. And that right there is a very bad point. That is not differentiable. Therefore, you can't, with the calculus that you guys know, there's nothing you can do with that. All right, so an example of a smooth curve would be something like this. Whee! Exactly, look at that thing. That thing is our favorite function. We miss this function. I don't know about you guys, but I love this function because it's a parabola. So much stuff happens, on a parabola. So parabolas are fun. All right. So what we're gonna also be concerned with is this idea of a unit tangent vector. A unit tangent vector is exactly how it sounds. It's basically just a vector of unit length. So what I'll do is I'll call that guy capital T, and capital T will be equal to the derivative of the vector, which you guys already know how to find now, and then the magnitude of the vector. Very similar to basically having the velocity and dividing it by the speed, if that makes any sense to you guys. Okay, and also make a note of this. This is a very important note. R prime of t is the tangent direction. And by tangent direction, well, what do I mean? It's basically like a line like that, but tangent to it. Let's see, darn, maybe that's not clear because of how curvy it is. Maybe I can exaggerate it. So it was like that. Still looks terrible. But I guess you guys seen tangent points before. It just basically touches it once and it goes off in another direction. Is basically what women do to men that they're not concerned about. If that makes any sense. All right. So far, so good. Let's minimize this bad boy. And let's talk more. Bam. All right. So we're going to say this. Maybe I can type this bad boy out. Tangent line to R of t at t is equal to t naught. Basically, what that's going to be is something that we've been doing for quite a while. It's going to be p, our vector p, plus some t times a vector v, where p is equal to r of t naught, and v is going to be the tangent direction. At t t of naught of r prime of t naught. And try to make it look legible for when Joe and Derek look at it, they can actually read it. There we go. All right, the best way to describe this is with an example. So, example, find the tangent vector, the unit tangent vector, and approximate line. And by approximate line, just like we were doing before in the world of, we'll say, calculus, we always find the approximate line, not the actual line, but we can approximate it within some error ratio. That's exactly what we're going to do here. The example is going to be as follows. It's going to be r of t is equal to e of t, comma, e of 2t, comma, e of 3t. And I really like, we'll say, e of t. E of t is probably one of the greatest functions in all of mathematics, in my opinion. And we're going to say that this is going to be at t of 0. The reason why I like the exponential function is because A, it blows up really fast. And also, when you take the derivative or the integral of e of the x or e of the t, you get the same thing back. And then if you add another value of e to the t, and you divide it by a specific e, you get the hyperbolic functions. And hyperbolic functions are the coolest thing in the world. Okay. You okay there, Jace? I can see that you're laughing a lot. She looks okay. Okay, all right. So the first thing we want to do is what we normally do. We normally take the derivative. So let's take the derivative of this bad boy function. And since you guys are so excited, I will do it for you because I'm such a nice guy. When we take the derivative of e to the t, we're going to get e to the t. If we take the derivative of e to the 2t, we're going to get 7e to the 2t. And if we take the derivative of e to the 3t, we're going to get 29e to the 3t. Amazing, right? Right there, all I did was I applied that amazing chain rule that you guys know and love to the derivative of that function, multiplied it by the normal function, and I kept my original e to the t because e to the t is just this, we'll say the same basically. All right, any questions at all? Okay, I think you guys are on the same page. So what I'm going to do is I'm going to make this even smaller. And let's see if the other one stays legible. Oh, that's pretty legible. I think that's pretty legible. Yeah. I see one head shaking like, yeah, it's legible. All right. Now, if we want to find a tangent vector, what we're going to do is we're just going to say when r prime is 0. So the tangent vector is going to be exactly where r prime is 0. So that means what we're going to do, and this is the fun part, we're going to plug that bad boy in for t. So that means we're going to have r prime of t. My apologies. I gotta sound like a mathematician. It's going to be r prime of 0 because we're plugging in 0. And we're going to have e to the 0, 2e to the t of 0, and then 3e of 3, 0. Now the cool thing is e to the 0 That bad boy is just 1. You could probably see why I like e to the 0 so much. And if we do 2 times 0, we get 0. And e to the 0 is 1. 1 times 2 gives us the 2. And if we do 3 times 0, we get 0. And then e to the 0 is 1. And 1 times 3 gives us the 3. I know, isn't that amazing? And now we have a vector of 1, 2, 3. And a vector of 1, 2, 3 is just basically a vector of 1, 2, 3. Cool. Now, watch. So basically what we found there is the tangent vector. Now if we want to find the unit vector, all we're going to do is take that specific vector that we just found and put it over the norm of that vector. So that's going to be vector 1, 2, 3 all over the magnitude of 1, 2, 3. Excuse me. All right, keep in mind, guys, I'm in the moldy room, so if you see me like coughing and I die, let's see. Since Ryan has his camera off, he'll be the one awarded my PS4. Yeah. Oh, look at that. I saw that real quick. Joey turned his camera off quick because he wants the PS4 too. Well, it's okay, Joey. If anything, you're going to get the brand new Nintendo Switch that's coming in the mail. All right. So watch. Now look what we're going to do. Well, the vector on top is still going to stay the same. But here's what's going to happen. We're going to have the magnitude of this, but we know how to calculate the magnitude. That's just the square root of 1 squared plus 2 squared plus 3 squared. And that gives us our unit vector. 3 squared is 9. 2 squared is 4. 9 plus 4 is what? 13. Plus 1 is 14. So we're going to have 1, 2, 3 all over the square root of 14. And I'm thinking, I'm going to say this is the final answer, but I think what some of you wrote in the test, Pearson didn't like because I think you left out the radical on the bottom. I think that's what I remember seeing or something like that. Like it asked for, I think it wanted the unit length, and then you wrote this, but you forgot the actual thing on the bottom. Unless I'm going crazy, it could have been another class. Remember, like I said on Pearson, it's very, very finicky. It wants a specific answer. If this was WebAssign, it would have been even more specific and more yucky. All right, so that's how we find the tangent vector and the unit tangent. Now, let's say we want to approximate the line. You want to approximate what's going on. So that means we're going to have to say, okay, is it roughly within this like realm of values? So watch how we're going to do that. To do that, we have to approximate the line. Let's make a nice little barrier, and we'll say approximate the line. You guys are used to approximating lines because you guys are amazing. So we're going to approximate the line. We're going to say P is going to be equal to R of 0. Now, this is very, very important because I've seen it happen all the time in Cal 1, and I've seen it happen in West Virginia University also when I was teaching Cal 3. They approximate the line, but they don't put it into the original function. Make sure you take the original function and you use that as your basis when you're approximating a line. I'll say it again. This is recorded, which means I know if I rewatch it, you guys heard it before. When you approximate the line, when you're approximating anything, you want to use the original function because we're looking at the original function. We're not looking at the derivative of the function. I think you guys went through this in Cal 1, where when you were curve sketching, you had to curve sketch the actual derivative. The derivative is a different type of graph than the original function. Therefore, you have to use the original function when you're trying to approximate the tangent line to the function. or else you're approximating the derivative function, which is not good. Okay, I think I could be as forceful as that is. Actually, so what we're going to do is this: we're going to approximate the point p. We're going to say p is equal to r of naught, and we're going to take the v vector that we just found, and that v vector is going to be 1, 2, 3, because that's the vector that we found. That's the tangent vector that we found. And now we're going to take the original function and plug in 0. And what's the original function? Let's see, I'm going to call on someone. I'm going to call on Joey.
You repeat the question, please. Sorry.
Not a problem. What is the original function?
1, 2, 3.
Ah,
It's
gotcha.
the E1. It's the E1. It's the E1.
Which E1?
The E to either 0, 2E is 0, 3 is 0.
Are you saying this line right here?
No, I'm saying the one above
This
the
guy.
little one.
All
That
right,
one, yes.
perfect. All right, just checking. All right, just wanted to make sure we were on the same page. We're gonna have r of 0. That's going to be equal to e to the 0, comma, e to the 2 of 0, comma, e to the 3 of 0. And those e's, well, that's just e to the 0, e to the 0. So that means we have a vector of what? Well, we have a vector of 1s. Gotta love those 1s. I don't know about you, but I think 1 is kind of cool. And now, to finish it off, this is the amazing part right now. We're going to say that we're going to build this point. The point we're going to use is the point that we just found, because that's the point that we want. So that's going to end up being 1, comma 1, comma 1 plus t times our vector. And if we want to parameterize that bad boy, we want to say this. We want to say, this is what I'm going to say. Therefore, I like those therefore, it's like a sharding gun. Therefore, L, which is a line, is going to be 1 plus t, comma, 1 plus 2t, comma, 1 plus 3t, comma, and then we put it in our vectorized form. And of course, we can say x is equal to 1 plus t, and y is equal to 1 plus 2t, and z is equal to 1 plus 3t. Drop the mic. And as scary as that seemed, this one problem took 30 minutes. It's okay. Because now we can actually start doing the Cal 3 that we came here for. Gave you guys all the background information that you needed. Now the Cal 3 comes like that. All right. Before I delete this bad boy, are there any questions at all?
I do actually.
Yes.
Professor, this might seem kind of like a basic question, but why is the point in vector notation?
Why is the point in vector notation? Are you saying, oh, I see what you're saying. So that point has to be in vector notation because we found it in vector notation. Because what we're going to do is we're going to include the points, a single point, and we're also going to say we could have a plane. That's what a vector is. A vector could also be a plane. So right there, what we're creating is that mysterious thing that you've been seeing in Pearson for a bit. They've been talking about the gradient for a bit. This right here is the main idea of the gradient. The gradient could be a line, could be a point, and it can also be a tangent plane. Because what we're going to have is we're going to have an x, a y, and we're going to have a x, a y, and a z coordinate. So what we're going to have is going to be exactly what were doing in Cal 1. You had a specific line, and now we can have lines and we can have tangent planes because we're in 3D. That's why we're going to make sure we're going to vectorize that point.
Okay, so just because it's in vector like form doesn't necessarily mean that it's a vector. It could, that's why
It
it's
could-
like that.
It could be a single point as well. And it
Okay,
can
thank
also
you.
be a tangent plane.
Mhm.
It's going to be like basically think of it as a world sheet, if you know what a world sheet is.
No, sorry.
So a world
But
sheet
okay, but I
is
get it.
you see this in physics before. Have you ever like whenever they talk about gravity, when they talk about gravity, they describe gravity as being curved space-time. So if you can imagine the gravity wrapping around the one ball, that right there is a specific world sheet that's wrapping around the ball. Think of it as it's displacing that specific area. And you're smiling like you're like, Professor, I don't want to know that, but thank you.
I don't know. I don't think I remember that from physics. Joey, did you? I
Ooh.
don't. Yeah, I don't think that's how they describe gravity to us.
Oh, okay. Oh, I'm sorry.
But
Okay.
now I know. Thank you.
Yes, yes. So yeah, remember, guys, I also study black holes. So yeah, yeah. It depends on who your professor was, because your professor could have been looking. He could have been like a climatologist, or he could have been like a astrophysicist. Well, if it was astrophysicist, he would have probably described it
He
that way
was
also.
a mechanical engineer.
That's why. Sorry, I'm not bashing mechanical engineers. Yeah, but it's okay. All right. We're not going to talk about your professor's shortcomings. We're going to just move on to the next question and pretend I didn't badmouth a professor. Oh no, this is being recorded. Oh no. Okay. Hopefully no one watches these recordings but us. All right. So if you don't see me here in 2 weeks, it's because I got canned. All right, here's number 2. We're gonna do another one. And that other one that we're gonna do is gonna be a very, very interesting function. The reason why it's gonna be interesting is because it's going to have our best friend in it. Not e to the x, but I think everyone's best friend in math is this type of function. 2 plus the cosine of t, comma, 3 plus the sine of t, and we're just going to throw t at the end. And we're going to say that t of naught is going to be pi over the 2. So watch. What we're going to do is, first thing we're going to do is we're going to take the derivative of that bad boy. If we take the derivative of this bad boy, we do it component-wise. Derivative of cosine is going to be minus sine of t, comma. Then we take the derivative of sine. Of course, that's going to be cosine of t. And now for the very hard one, I know you guys can't handle it, but I'm going to show you that you can handle it. The derivative of t, that's going to be 1. Isn't that amazing? Now, once we do that, the next thing we're going to do is we're going to evaluate the tangent vector at our specific point. The last time our point was 0. This time our point is going to be pi over 2. So we're going to say r prime of t. I keep doing it. Sorry, guys. R prime of t is going to be r prime of pi over 2. And the r prime of pi over 2, okay, that's like a really bad pi over 2. Going back to virtual for today is showing how much I haven't used my wrist in a while. All right, so if you put the sine of pi over 2, well, the sine of pi over 2 is going to be 1. Well, we have a negative in front of the sine, which means we're going to have a negative 1 as our value. And I'm going to put the cosine of pi over 2. And the cosine of pi over 2, we know that bad boy is going to be 0. And then the 1 of pi over 2 is just basically 1, because you can't really plug in a pi over 2. It's just 1. And that's going to be our tangent vector. So this right here is our tangent vector. And now our next step is we're going to find the unit tangent vector. I should type that out also. Unit tangent vector. Unit tangent vector is basically what we're going to do is we're just going to take r prime of our point. In this case, our point is pi over 2 divided by the magnitude of that specific point, or in this case, that specific vector. So we're going to have the vector of -1, 0, 1 all over. Well, this cool thing is we know is going to be -1 squared, 0 squared, and 1 squared. 1 squared is just 1. 1 plus 1 is 2. Plus 0 is 2. Square root of 2. Keep in mind, guys, 2 plus 0 is 2. I only say that because my other class made that mistake. They put that 2 plus 0 was 0. And I was like, this exact face. Yes, it was terrible. So make sure you guys don't do that same mistake. Any number plus 0 is the same number itself unless you're working in a specific group and doing group theory. But you guys are not doing group theory at all, unless you want to, which I could instruct group theory also. Group theory is actually really, really fun. Group theory basically is really, really fun in the world of physics, because what it does is it describes physics that we cannot talk about in a real world scenario. Basically, quantum theory is uses the ideas of group theory because it describes it better. That's when we're going straight towards like supersymmetry theory. All right, so now we know we're going to have a specific point. The point we're going to take is from r of pi over 2. And I stress that as much as possible, because what we're going to do is we're going to use what function? Let's pick on David. David, what function are we going to use to approximate our line?
2 plus cosine t.
And 3 plus sine of t and t. Yeah, perfect. Good job. All right, cool. All right, so when we use that, we're going to plug that bad boy in. What's the cosine of pi over t? And let's see, let's not pick on David. Let's pick on Jace. Jace, what is the cosine of pi over 2?
0,
0. And now 2 plus 0, Jace?
2.
Thank you. Just checking. See, she was paying attention. I'm proud of her. 2. All right, then if we plug in pi over 2 times sine, well, Mason, what is pi over 2? What is sine of pi over 2?
0. Or 1, sorry.
1. Perfect. So sine of pi over 2 is 1. And Mr. Mason, what is 3 plus 1?
4.
4. Perfect. Just checking. And now, to finish this off, Mr. Ryan, if we plug in pi over 2 to t, what do we get?
Pi over 2.
Pi over 2. Awesome. Cool. And then what we're going to do is, well, we have our vector already. The vector we have is just going to be -1, comma 0, comma 1. And we're just going to throw it into a line form. The line form is just going to be 2, 4, and pi over 2 plus t times the vector of -1, 0, and 1. So far, so good, right, guys? Then we vectorize it. To vectorize it, or we'll instead of calling it vectorize it, let's call it lining it. Get it? Lining it. Okay, that was bad. It's just going to be 2 minus t, 4, and then pi over 2 plus t. This is me playing numbers. Any questions about that? The cool thing is, I only think 2 examples is enough to get this point across to you guys. Because A, you already seen how to do this. You already know how to do that. This you already know how to do. This is something that I stressed at the very beginning. The only thing that's brand new is just taking the derivative component wise. But you guys are so good at taking the derivative, you don't even need to worry about that. So basically what you do is you take the first derivative, you plug in the specific value of it, get your vector, take the unit tangent vector, just because we're asking you to take the unit tangent vector. You don't really need this, but I think the way Pearson sets it up is they want this first and they want this second, and they want, I believe, this next. So they just want you to go step by step by step because they're annoying. But this is the process. Basically, you're supposed to go from here to here, and you're good. All right, cool. Like I said at the very beginning, we're going to breeze by the calculus 3 because we already have the necessary background that we need. All right, and then one more last thing that we're going to look at is this thing that we wanted to look at for a while, arc length. Now, arc length is extremely difficult in the sense of actually taking a look at most of your, we'll say, like most of your curves and stuff like that. That's actually hard to take the derivative of. That right there, sometimes the specific function that you want to graph with, like if you want to find the arc length of it, you have to use complex analysis. And this is a real analysis course in the sense that Cal 3 isn't over the real numbers. When we give you these functions, we're going to try our best to make sure that these functions are differentiable over the real numbers. We're not going to give you functions that are not differentiable over the real numbers and differentiable over the complex world. Complex world, leave that for me. You guys will see that probably never in your life. The only person that's probably going to see that is Mason when he goes deeper into his physics. Other than that, you engineers, you won't see much of complex analysis. You'll probably like apply a complex analysis in like a program, but you won't do it by hand unless you're probably dealing with like Spacely sprockets or like who's that guy that just I think is retiring, Musk. Unless you're working for Musk, you'll probably see that. All right, when it comes to arc length, what we're going to do is we're going to suppose a smooth function or a smooth curve. And the cool thing is, of course, we know that it could violate the vertical line test, but we're going to try to make sure that we don't violate that at this point in time. But functions could violate the vertical line test. They just aren't the functions that you're used to looking at. All right, so what is arc length? Well, you guys know what it is, so I'm going to give you a, we'll say a simplified definition. The arc length of a smooth curve over the interval AB is given by, and sadly this I have to write out because we need our best friend, the integral of r prime of t dt. And you've all seen this before in Cal 1, if not Cal 2, it's coming back with a vengeance. But arc length is actually very, very, we'll say, we coddle you, basically. Okay, so let's do a specific example. Let's keep this definition on the board. Let's just minimize it. We're gonna need a lot of room, so maybe minimize it like that. Okay, the example. And this one is going to be an easy example because easy is good. So R of t, that's going to be equal to, we're going to look at the cosine of t. We're going to look at the sine of t. And let's just close it there. We're going to say 4t in this nice interval of 0 to 2 pi. Now watch what we're going to do. We're going to take the first derivative, and I know you guys can calculate that first derivative. That first derivative is just going to be minus sine of t and cosine of t. And then we're going to take the, we'll say, the magnitude of it. When we take the magnitude of it, we're going to get r prime of t. And of course, we know what that magnitude is going to be. Well, we're going to take the square root of sine, negative sine of t squared plus cosine of t squared. And now, for a nice high five, next class, what is this equal to?
1.
1. I guess Ryan's getting that high five. The reason why it's equal to 1 is because if you square sine of t, you get sine squared of t. If you square cosine of t, you get cosine squared of t. Remember, you only square the trigonometric function, you do not square the t. Don't square the t. I've seen this happen way too many times. They're in Cal 3 and they forget the simple stuff, which is okay. But try not to forget this simple thing. That when you square sine of t, you get sine squared of t. You square cosine of t, you get cosine squared of t. And that bad boy ends up being equal to the square root of 1, and the square root of 1, of course, is 1. So now, if you find the arc length, well, let's find the arc length. To find the arc length, what we're going to do is we're going to take the integral of the magnitude. You can see why I made it so easy for you guys. Maybe from 0 to 2 pi of 1 dt. You take the antiderivative of 1, what do you get? Well, you get t. Going from 0 to 2 pi. And if I evaluate that, that's basically 2 pi minus the 0, which gives us 2 pi. Now let's just think about this function. Well, if you think about this function, cosine of t and sine of t, we've seen this before. Cosine of t and sine of t, that bad boy is just a circle, right? Right, it's just a circle. Now, let's pick on someone. Let's pick on someone that in case are surrounded by fire at the moment. Miss Jace, if we're looking at arc length, what are we looking at in this world?
The circumference.
Circumference. Isn't it safe to say that the circumference of a circle is equal to something very specific? And what is that specific thing that is equal to? Or should I say this? What is the formula for circumference?
2 pi r.
2 pi r. What is this? What is the magnitude of our vector? just 1, right, Joey? Is just 1. So that means there's going to be 2 pi times 1, right? And what's 2 pi times 1? That's just 2 pi, right? Isn't that just what we just calculated? Right, makes sense. So we could check ourselves with just inspection. And I believe that's what Pearson wants from you. They want you to verify a graph like visually. Because some of the functions that they're going to give you is actually very, very hard to do by hand. If it takes me 15 minutes to do it by hand, I think it might take you guys maybe the same amount of time or even longer. So yeah. And this is something that if I was to put this on your next exam, which I believe we said which was which day, guys? Was it the 21st I said?
I think it was the 28th.
The 28th. Ah, okay. Oh yeah, that makes sense. I told you guys 2 days ago, which is a full month. Yeah, the 28th. Awesome. Sounds great. All right. And when we come back from vacation, I'm going to give you guys a project. Remember, there's a project grade that you guys are going to need. And I say by need, I say some of you weren't thrilled with your test grades, which is okay. But that project will bring your test grades up. Well, not bring your test grade up, but bring your grade up overall. I think that's something you guys really want. I can see Joey shaking his head like, yeah. And he's probably going to put some demon skulls up like, yeah. Exactly. All right. So let's see. We have approximately 9 minutes. And if we go over a bit, is that okay with you guys? Okay, I see a nod from Joey. I see a disappointed face from David. Maybe not. That's a smile. I see smiles from everyone except for Ryan, but I'm going to assume Ryan's also smiling as well. All right, because now it's time to do even more real calculus 3. Now we're talking about something very, very important, which is going to be the bulk of the rest of the semester. Functions of several variables. This is what we're leading towards. Functions of several variables. So in the world of calculus, in the world of Cal 1, you were doing something called single variable calculus. You was not even doing correct or real calculus. No offense. You was not doing real calculus. You was just doing the watered down version of calculus. What do I mean by the watered down version of calculus? Well, you were looking at f of x is equal to x squared, or you're looking at f of x is equal to sine of x plus 3. You was looking at stuff that dealt with single variables. That's not interesting at all. Although how hard Cal 1 and Cal 2 was, that is not interesting at all. That's kind of boring in a way. I think the only interesting you guys had was a few optimization problems. Oh, let's make let's optimize the best space for these ring dings. Like really? I'm sorry. I apologize. To me, I find that quite boring. It means nothing. Like if I want to do optimization, I want to land a spaceship at a space station. That's the type of math I want to do. Or if anything, type of math I want to do is I want to shoot up, we'll say, perfect. We'll drop down depth charges to take out an enemy submarine. That's more interesting. Or I want to intercept a bunch of ballistic missiles with my own missiles or my own cannon. That's the type of math I want to do. That is Cal 3 right there at its best. Or even better, I want to figure out how to stop the zombie apocalypse with my math. Because right there, that's a growth rate. That growth rate is exponential. You know, it happens like that. So this whole COVID panic that we had was because whoever was taking care of those numbers was a zombie apocalypse enthusiast. That's why we were suffering so much, because they were like, "Oh no, the zombie apocalypse." Yeah, no, I'm kidding. But that's one scenario that we have in our heads is, hey, if the spread rate is so easy, if the infection rate is so easy, everybody's going to get it like that, especially in the populated cities. So that was the motivation for that. All right, but now we're doing Cal 3. What is Cal 3? Well, Calculus 3 is probably the greatest thing in the world. We're going to take an input value. Our input value is going to either be x plus y or x, y, and z. And when we plug these bad boys in, guess what we're going to get? Well, our output, and this is where it becomes extremely interesting, our output is a single number. We're taking these complicated functions and we're spitting out a specific number. Before we were spitting out a specific vector or a specific tangent line. Now we're spitting out a specific number. This specific number could be the difference between, and I'll use his name loosely, John Glenn coming back down to Earth from space about 70 years ago. This is that difference right there. That difference of basically taking an elliptical orbit to a parabolic orbit. Basically, we wanted to drop down and fall into Earth so we can find our no-go and go zone. That's what they were doing. And they applied a formula called Euler's method to do that. They were finding a specific value, a specific spot, a specific time interval for him to come back down to Earth on that prehistoric space shuttle or prehistoric rocket. All right, so in the last time remaining that we have, we're gonna do a specific example. You're gonna love this example. It's gonna be so hard, but you guys will pull through because you're just amazing. We're gonna have f of xy is equal to x squared plus y squared. And and a quick side note. Remember how when we learned in single variable calculus, we had y is equal to like mx plus b? Or even before that, and we said, hey, guess what? This bad boy can be f of x is equal to m of x plus b. We're going to do the same thing here, but technically our this function right here is going to be it's going to look something like this. Z is equal to x squared plus y squared. So what we're going to do is we're going to reserve z to be f of xy. Basically, it's taking these two values at the same time. So now watch. What we're going to do is this. We're going to look for f of 0, 0. I know it's hard, but you guys can pull through this. If we take 0 and we square it, and we take another 0 and we square it, and we add those two together, what do we get? 0, exactly. Now watch this. We're going to do f of 0, 2. F of 0, 2 is just basically we have 0 squared plus 2 squared. That's going to give us the 17, right? Oh, good job, Joey. He corrected me. He's like, oh no, professor, it's 4. And then here's the hard one. We do f of 2 comma 2. Well, f of 2 comma 2, that's going to be 2 squared plus 2 squared. I know you guys are cringing right now, but don't worry. That number is just 8. Drop the ring ding. Pull out the box. Drop the ring down. Amazing. Now, I'm going to go a little bit over. But let's do one more example just to beat that into your head. This example is going to be this. Is going to be f x, y, z. F of x, y, z. That's just going to be equal to 8x plus 3y minus 4z. And what we're going to do is I'm going to say, find me f 0, 0, 0. And I know you guys are going to have a hard time with this, but don't worry. I'm here for you. What is 0 plus 0 plus 0? 0. Exactly. Let's get a little funky here. Let's do 0, comma 1, comma 0. Well, that's just going to be, well, we're going to plug in 0 for x. That's going to give us 0. 3 times 1, that's just going to give us 3. 4 times 0 is just going to give us 0. So it's going to be 0 plus 3 plus 0, which is just 3. And then we could get even more crazy. We could say f of 2, comma 1, 0. Well, that's just going to be 8 times 2, which is going to give us 16, plus 3 minus 0, which is just 19. And then lastly, we went a minute over, and I apologize for that. Let's do f 1, comma 1, comma 1. That's going to be 8 plus the 3 minus the 4, which is going to give us a total of, well, that's just 8 plus 3 is 11. 11 minus 4, that's going to give us the 7. Lucky number 7. And like I said before, drop the ring down. Crunching the numbers like that, especially in a math program, they'll love you.
Cool. All right, sounds good.
All right, take care, sir.
Same to you.